Hello everybody, welcome to another Chem Complete episode, and what I would like to address today is an addition or an add-on to the HPLC series. So if you've been following the series, you know we've been going over some of the major methods for HPLC, such as normal phase, reverse phase, ion, and we've also discussed in great detail column chemistry, as well as the basics of HPLC and HPLC instrumentation. So because this is kind of an introductory course, with free content that I'm putting out there, I did want to have a brief discussion on band broadening. So that's part of what I would like to take a look at today in this lecture. I don't know if this one will be quite as long as some of the other lectures that I've put together regarding HPLC, but we are going to talk about what is band broadening, why is it a problem, in particular to chemists that are using HPLC, what factors contribute to it, and there's actually an equation we're going to take a look at. And that will help us kind of understand mathematically what may be going on there in a general overall sense. And then finally, we obviously want to know what can we do to minimize these effects. And sometimes the minimization can be a mixture of different moving pieces, and sometimes it's just that the column is worn out itself and you may need to replace your column. So we'll talk about all of that starting right now. So before I get too far into the content, remember you can always visit us over at chemcomplete.com, and there you can pick up guides and resources, HPLC included, over in the guide section. That's a great way to support the channel. You can also find some free resources over there, and we will be expanding our site throughout the year this year as we continue to put out more free resources as well as paid for resources. You can find all the information over there to support us, and as always, commenting, interacting, dropping a like if you find this information helpful is always a great way to show appreciation for the channel. So make sure you hit subscribe if you're not subscribed, and let's get started. All right, so what is band broadening? Band broadening is a phenomenon when what should be really distinct separations and sharp peaks on your chromatogram are going to start broadening out or flattening. And sometimes this can get very bad because you end up having these broadenings that are sort of increasing and pushing against other peaks. And so sometimes you can get peaks that are almost merging together due to broadening. Now, broadening is not the only thing that could be responsible for that. You may have poor separation conditions and you need to kind of increase the retention time between those two peaks, but broadening can lead to issues similar to that. So when you see broadening, if you were to take a look at a normal peak, you'd probably come across and see hopefully something on your chromatogram that's somewhat sharp and distinct. It's not a single line, so there is some result of very minor broadening as you don't have one individual signal, right? And that's because as we load content onto an HPLC column, the hope is that the analytes initially start as this narrow band of material as they go down the column, but they are going to kind of widen out a little bit due to factors that we'll talk about here. And so what happens is not all of the content hits the detector within a very short period, right? Ideally, that's what would happen, but we do kind of see a little bit of extenuation there as some natural processes tend to occur. Now, obviously, this becomes more and more problematic the further and further this gap becomes. So if we're traveling through the column here, right, and this is the analyte of interest that we're looking at, the further apart or the wider the band kind of diffuses, the more problematic the broadening can become. And so then you may end up starting to see stuff that looks like this instead of a nice sharp peak, and you get broadening of the band, both in the chromatogram printout, and that's really a reflection of what's going on inside the column. Your actual band of analyte that should be migrating across the column, right, is kind of flattening or spreading or diffusing out and causing this problem here. So what is really the issue outside of the fact that the peaks occasionally may run together? What is the problem here? Okay, well, number one, when you're using HPLC to purify mixture of components, these analytes will often come out mixed together. So that is not good, okay? If you start having broadening, in other words, let's say that it should look something like this, right? And they're kind of close together, but they're distinct separate peaks. And then you start getting broadening happening, right? Where you've got one, and then the other one, before it really comes back down, starts to shoulder off of it like this, okay? This is far more ideal, this scenario over here, versus this one, right? Especially if we're not kind of returning to that baseline or as close to the baseline as possible. And so one of the big issues, as I just said, is when you're trying to purify the analytes, you could end up having the analytes mixed together. Okay, so analyte mixing. And that's obviously an issue because when we're doing chromatography, the general goal of chromatography is analysis, but it's also purification. It's separation of materials and analytes from one another. So the concept that we're now going to have to wrestle with is, are the analytes separated well enough, or are they starting to bleed together some, right? And it doesn't mean, because normally what will happen is if you're interested in purification, you'll collect what's called a fraction. And so there may be certain fractions. Let's say you collect some right here. That's some of the analyte. You collect another fraction from here to here, right? Maybe it's one every minute or every 30 seconds you're collecting a fraction, right? But at some point, when you get to this area right here, you're going to have fractions that are mixed together. So you're not going to be able to get true purification and kind of maximizing your purified compound or analyte coming out. You're going to have some that inevitably starts mixing together if this shouldering issue is occurring, right? And so number two, one of the other issues here, whether there's kind of a crossover between analytes or not, is it could potentially lead to the inability to quantify your results properly, okay? So inability to, and I'm just going to put quantify here. So remember, quantify means to use numbers. And so if we're talking about, okay, the broadening effect here, it may lead to issues where when you're trying to analyze your individual analytes that have been broadening to a severe extent, you're not really going to be able to quantify them properly relative to other analytes in the mixture. And that's a problem, not necessarily so much about purification, but about analysis and quantification, being able to say, hey, this mixture is 22% of this analyte, right? If something is sent in and you're kind of analyzing it based off of standards that you're making and putting into your HPLC system. So those are the two major problems or issues that typically can come across, right? So when band broadening occurs, it is important to keep in mind, because we're going to start talking about these issues here. Band broadening will occur naturally as a column ages. So your stationary phase, your column, the more runs you put through it, and certainly the harsher the conditions for those runs, or the longer the runs take, you are going to wear the column down. You're going to wear the stationary phase down, and you can end up having issues. So if playing or tinkering around with these things that we're about to talk about, these different factors, don't seem to work, then there is a probability that you may need a new column. Okay, so I don't want to rule that out and think, oh, just for saving money, we'll just constantly keep playing with these other factors. It may be that you need to replace your column, especially if you've had it running for a while. Okay, however, that being said, there are several ways that we can attempt to minimize band broadening. So let's study the factors that can play into it outside of just an aged column, and then we can talk about minimizing those factors. So let's get started with that by introducing an equation first. Okay, so the equation is going to be referenced or spoken of as the Van Deemter equation. Okay, so the Van Deemter equation is a way that we can kind of tie together band broadening in a mathematical sense. And there are 4 variables that play into the broadening effect. Okay, so what we can do is we can say H is going to generally represent the broadening effect. So the larger H becomes, the greater the broadening effects are going to be. Equals A plus B divided by U plus C times U. And this is our equation here that's going to help explain the broadening effect. Okay, so obviously the next question we have is, well, what is A, B, C, and U, right? Because that's all going to affect H, and H is a reference to height involving theoretical plates and how much broadening is going to occur. But what are these other individual factors, right? So there's 3 of them, and we will list them here, starting with A, and we'll move forward. Okay, so the first one is something that is known as multipath diffusion. And multipath diffusion is sometimes referred to as Eddy diffusion. Okay, so I'm going to put that in parentheses here, and that's spelled E-D-D-Y. So you may very commonly come across this referenced as Eddy diffusion. And this is A. This is component A in the equation here. And we will discuss what that is after we list all of these. So I'm going to list B, C, and U, and then we'll go into a detailed discussion. What is multipath diffusion? Okay, so let's go to number 2. So number 2 on the list, B, is what we would call longitudinal diffusion. Now, longitudinal diffusion is really, you could say, random diffusion, natural diffusion. This is a process that is going to occur throughout nature. Okay, so when you have something that is in a high concentration in one area, the tendency is for it to spread out to areas of lower concentration. That is longitudinal diffusion. And so that's the second factor. And then factor number 3 is going to be what we would refer to as mass transfer. Okay, and again, we're going to go into more details here in a minute. The mass that we're referring to here is the analyte and how often it's transferring back and forth between the individual particles in the stationary phase. So keep in mind, if you looked at our lecture on column chemistry, you know that there are little small individual particles packed in most of the columns. Now, a lot of times they have some sort of addition or layer on top of them, right, in order to provide better separation, like a C18 column or something. But when you look at the bottom, there are still these particles, these little beads, if you want to call them that, right, that are there. And so the question is, how quickly or how rapidly is the analyte mass transferring particle to particle? And is it all the same? Because it turns out that it's not always the same, and we'll discuss why in another minute here. Okay, and then number 4, which is the last one, this is U on the list there, and that is going to be what we would best refer to as the linear flow rate. Okay, so one of the big terms that we always talk about in HPLC is flow rate, and that is referring to, okay, how quickly are we pumping the mobile phase through the stationary phase, at what rate? And we're usually talking here about a amount of volume per some time. So maybe we're talking about 5 milliliters per minute or 2 milliliters per minute. Or whatever the given unit may be. We're talking about the flow rate of the mobile phase through the column. And this is going to be a bit trickier. We're going to tie it in at the end, because it turns out that flow rates, you can see in the equation here, okay, A plus B plus C, if A, B, or C all increase or get larger, then they're going to increase the broadening. But you can see there's an inverse relationship between flow rate with B versus C. And so that is to say, if you have a low flow rate for U, then that means you're going to have a tiny denominator and B is going to increase, but it'll keep C relatively low. And then if you allow the flow rate to increase or get larger, it's going to amplify C, the mass transfer, but it's going to help minimize or shrink down B. So there's going to be a balance here. There's no perfect answer, and you have to keep that in mind, that when you kind of use the cliche term in moderation, right? This may be a case where you have to think in moderation. The flow rate may need to be moderate so that we're not kind of maximizing or capitalizing on either of the factors, longitudinal diffusion or mass transfer. So keep that kind of tucked in the back of your mind as we're walking through this and talking about it. All right, so let's start with a discussion on multipath diffusion. So multipath diffusion is really talking about when you have a column, and in that column you've got your various packing material, okay? And I'm kind of zooming in on this here, right? So this is your packing material, your beads for the stationary phase that are here. If you were to look, analytes that are coming through in a band could take different pathways, right? So you could have an analyte that's coming through that kind of goes through the top here. You could have another one that's coming through that goes underneath and then above this area, comes out here, goes all the way underneath here, right? And then arrives here. You could have another one, let's change the color just so it's a little bit easier to see here. We'll use blue here, okay? That could start out, right? And the idea is that this is all the band that's initially loaded here, right? And this one decides that it's going underneath here, then it's going to travel over top, then it's going to go right in between here, right? It's going to come up right over here, down, and then finish through here. Okay, so I think you can probably see why this is called multipath diffusion. It's because when we take a stationary phase and we attempt to pack the particles in there for separation, there is the potential that there could be multiple paths that these analytes can take. And if they take multiple paths, they're going to be crossing over different amounts of surface area, and that as a result means that you could have some broadening as they're all trying to make their way through, right? So imagine that some people, if you're kind of racing around, let's say a classroom or a building, and you've got a lot of obstacles in the way, chairs, tables. Some people can run straight through the middle aisle to the back wall. Other people have to weave in and out of those chairs and those tables. You're not all necessarily going to hit the wall at the same time, right? So you're going to have some separation. You're going to have some people that are finishing before others. Well, it's the same is true of the analytes here. When you have multiple pathways, and the more pathways you have, the more of this diffusion can happen. The greater A is going to increase here. Okay, now it's important to note that in theory, A could be reduced to 0 and could not contribute. But the theory behind that is that you would need a tubular column that really doesn't have any type of packing in it. And so that sort of defeats the purpose, because we pack our columns to give additional surface area and the chance to add these additional layers, right, or modifications on top for better separation. So it's a bit counterintuitive to say, oh, I'm going to do chromatography and I'm really just going to kind of let these guys separate out without a whole lot of packed material in there or any sort of intermolecular force interactions that are going on the column. So in theory, A could drop out, but in reality, you're probably going to be dealing with the multipath diffusion factor to some extent. All right. So that leads us to B, which is number 2 on the list, the longitudinal diffusion. All right. Now, as I stated before, longitudinal diffusion is a natural process in which you're going to have high concentrations of analyte particles that are just simply going to statistically spread out and move from areas of high concentration to low concentration over a period of time. Okay, and this can oftentimes be a result of excessive time on the column. Okay, so we're talking about B here, the longitudinal diffusion in this equation. So if there is excess, if there is excess time, and again, this is a relative term, right, on the column, this can become problematic. And that is because this process is going to occur naturally. So the more time that you allow a band of analyte to spend on the column, the more the longitudinal diffusion can take hold and start moving about. So unlike the multipath diffusion, which in theory, again, it's very theoretical, could drop to 0, the longitudinal diffusion may not drop to 0 because the very laws of thermodynamics and the way that concentration is going to spread with analyte particles would kind of be violated if you could somehow get this to 0. So again, the idea is that, right, we've got a band of analyte. These particles are highly concentrated in one area, right? So this kind of represents our band of analyte. If each of these was an analyte particle, right, and here's our column, and they're moving along. Well, the more time that they spend, they're not going to want to stay all together in this area. They're naturally, after some time t, going to be more diffused and spread out from one another. Now, that doesn't mean they're spread out over the entire column, right? But it does mean that this band that was once very tight and narrow is going to start to broaden out. And the more time that I allow that material to spend on the column, the more the longitudinal diffusion is going to occur, right? Now, there's kind of a limit to this in the fact that if it spreads out, it's still going to be interacting with the stationary phase, and so separation will still occur to some effect. It's going to kind of move as a group based on its retention time and its intermolecular interactions with the stationary phase. But having really long run times can be problematic here, okay? So you're going to end up getting that diffusion, and it's going to naturally start broadening if there's too much time that's being spent on the column. And you do have to watch flow rates here. So when we start talking about your flow rate, okay, and we'll talk about this more in the how do we minimize section, but if you go back up here and you look, having flow rates that are relatively small, which means a low flow rate, okay, is going to increase this number. So what does that mean? Let's think about that logically. If my flow rate is very tiny, let's say it's 1 milliliter per minute or half a milliliter per minute, okay? If this is a tiny number, then B is going to balloon up. It's going to get larger in its factor. And that makes sense because what happens is if I keep a very low flow rate, it's going to take a long time to flow or push material through the column, right? If I'm only pushing 1 milliliter a minute through, it may take a whole lot of time until I get to this analyte. Whereas let's say that I'm setting it at 3 milliliters, 4 milliliters per minute. Well, then I'm having a bit of a quicker movement over the stationary phase with the mobile phase. And so there's not as much natural time for this longitudinal diffusion to take effect. And so it's going to shrink that B term. Okay, so the time on the column, and as a direct result of that, keeping very low flow rates can be problematic there. And we'll kind of summarize that up as we continue to move along here. Okay, so let's talk about the mass transfer. So this is C on our list, number 3. And when we start talking about mass transfer, this factor is going to relate to the fact that all of those particles that we pack into the stationary phase, so the actual, be it silica particles or whatever stationary particles you're putting on there that may have modifications, those individual particles or beads are generally going to be porous. And the reason that they're going to be porous, okay, is because that will increase the surface area. So one of the things that we want in order to get good separation from analyte to other analyte, not within the group of analytes themselves, okay, is we want good surface area. Because if we have decent surface area, there's going to be more opportunity for the intermolecular interactions, and that means that hopefully we can get some nice separation and clean retention times, keeping analyte A away from analyte B, or analyte 1 away from analyte 2, and they're not just kind of all clustered together there. Okay, but this can work against you when you're looking within the same band of analyte. So let's say analyte 2 is going over these porous surface areas. Well, they're not completely uniform, and so certain analyte particles may get stuck or go down into the pores further than some of the others. And so this can create a situation where some of your analyte in a given band may end up moving generally over the top of the surfaces of these packing materials. And they're not really going to have much interaction within the pore. And then you're going to have some that can go partway into the porous material, right? And then you can have some that are going to go even further deeper into the porous material. And so a lot of the images that you'll see that kind of set this up, it almost looks like a Pac-Man image, okay? But you've got sort of this bead here that's got the pores in it, all right? And then these are the modifications. If you look at these little hair-like structures, right? These are your C18s or whatever coming off here. And so what you want to kind of keep in mind, and let's bring this actually all the way up here, okay? That'll work better for the example. What you're going to see here is that if your analyte is sort of coming across as a band here, right? And it's starting to move over top of this, it is possible that some of the analyte is going to kind of take this pathway here and it's not really going to go into that pore. But it's possible that there's going to be another version of that analyte. Let's pick something different than blue here so we can see it. We'll do the purple. And that's going to come across, and that could potentially go down inside of here, exposing it to more surface area and giving it a longer runtime over that particular stationary phase particle. Okay, and so this is the general concept of mass transfer, is as we're jumping particle to particle, or we're literally taking the mass, the analytes, and moving them along the column, how long are they spending and how often are they transferring back and forth between the particles? Well, that can be a factor here. We need to consider the fact that most of these particles, the stationary phase particles, are porous, and so the analytes may have a different amount of time that they're spending in each of these various pores there, okay? And so to wrap up, as we're kind of talking about this before we get to minimizing it, what you can see here is the flow rate now multiplied with the mass transfer factor. And that is because if you take a very short amount of time, right, this number is going to be low. So that is to say, if this value right here, your flow rate is low, let's say 1 milliliter per minute, right? If it's moving slow enough, then the movement of the red analyte to the purple analyte really isn't going to make a huge amount of difference because the red analyte's not being pushed through that fast in comparison. Okay, but as we start to rapidly increase and U starts to climb, meaning our flow rate is increasing, we keep bumping it up, well now the rate of the one that is not interacting with those pores may start to separate out quite a bit ahead of the ones that are taking that extra porous trip through the packed material. And again, you can see how flow rate is playing in here. There's probably a balance between factors B and C here in the equation, right? So when we look at the Van Deemter equation, it's really a mix of all of these that are going to be playing a factor here in regards to band broadening. All right, so what we want to address now that we kind of can visualize and conceptualize what each of these are, let's talk about for each of these how we can limit or minimize the effects that are being played here. And you're going to see some common themes. So let's go ahead and start with that. So how do we minimize band broadening? Here's our list that I just brought up. Now please keep in mind these are general suggestions, so I cannot give you a specific column length or a specific flow rate here because some of that is going to depend on the particular solution that you are trying to separate and what those results look like. Okay, but they are general principles to keep in mind when you are working with HPLC. So number one, or letter A in the equation, how do we handle multipath diffusion and minimizing that? Well, a lot of that is going to be on the producer of the stationary phase on their end. So when you are purchasing your columns, it is very important that you are going through a reputable company and one that you have a good relationship with and you can trust in terms of their processing. So number one, you need well-packed columns, because if the columns are not well-packed and the stationary is not, the stationary phase is not well-packed, that's going to leave larger openings between the particles, which is going to allow for more pathways that the analyte can travel, which could potentially start separating out and causing multipath diffusion. Okay, smaller stationary particles are better. That is more within your control. Many times when you select a column, you can pick the general particle size that you are going to have shipped to you. And so generally speaking, going with smaller stationary particles is a better idea. And you're going to see that theme repeated here in a couple minutes, all right? So if you're confused about some of that, I would encourage you to go back to the lecture that I gave on the chemistry behind columns, which I want to say is maybe lecture 2. But go back through the playlist and check. And there's a discussion about stationary phase size, what's relatively considered acceptable, when you could run into pressure issues, things like that. Okay, and then the other thing you want to make sure is you definitely want uniform size and distribution of the particles that are making up the stationary phase. So again, you're kind of at the mercy of the column producer, okay, but obviously taking good care of your columns plays into this in terms of making sure they continue to stay well packed and that the distribution is good. Okay, so for the longitudinal diffusion, this is our random or natural diffusion process. Okay, moderate flow rates are best, and I make a note here, careful, not too high and not too low. Now both of these are important because if it is too low or too slow, okay, broadening can occur, and we already kind of talked about that earlier. But you need to be careful that it's not too fast either, because if it is too fast and you're trying to run away from the broadening, getting too fast with the flow rate can lead to back pressure issues and high pressure issues as you're trying to kind of force this mobile phase through the column faster than it should be going. So you do potentially have pressure problems if you're trying to go too high with the flow rate, okay? So it's not great to say, hey, I'm going to minimize all my longitudinal diffusion as best I can, but at the cost of creating pressure issues in the instrumentation, okay? That's just as problematic for different reasons. So when you get ready to use any sort of tubing, and the column is kind of beneath this, it's the same premise, you want to use the minimal amount that's required, okay? Especially if analyte is passing through or going somewhere. You want to make sure all your fixtures are correct, that you're connecting using the right fixtures, but you don't want excessive amounts of column length or tubing, and you want to try to keep the diameter reasonable, reasonably small, okay? Because the larger it becomes, the easier the longitudinal diffusion is going to take hold. And in terms of column length, that is a double-edged sword, because the shorter the column length, the less the longitudinal diffusion, but the longer the column length, the better the overall general separation is going to be, right? Because there's more theoretical plates, there's more chance for that separation to occur. But you have to be careful because that longitudinal diffusion, that broadening effect can come in. So reasonable is kind of a subjective term here. You need it to be reasonably long enough to separate out what your goal is or what kind of mixtures you're working with, but not so long that you're promoting broadening or unneeded time on the column. Okay, mass transfer. So for the last factor, smaller stationary phase particles are ideal. Again, we're reinforcing this concept because the smaller the particles are, the less the porous effects are going to be felt, and the less the gap in mass transfer is going to be between analytes that are not interacting with those pores versus those that are. Heating the column can help with this, okay? So heating, and again, you need to be careful because heating could potentially increase the longitudinal diffusion, so there's a balance. But some heating may be a good experimental technique to use and do some trial and error. That can generally help keep the non-porous and the porous particles a little more uniform in nature as we're moving them along, okay? And then, again, I put lower to moderate flow rates here instead of just moderate. If you can stay on the lower end of moderate and still not promote too much longitudinal diffusion, that's a good idea, because the higher these rates go, the more the mass transfer effect is going to play into this, all right? So that's it. I'm going to wrap it up there. That pretty much discusses what I wanted to talk about for band broadenings. What is it? Why is it a problem? What plays into it? As well as how can we attempt to minimize it? And there's some practical solutions here that you'd have to play back and forth with when you're working with your HPLC factors. Okay? So that is it for me. Again, one more shout out to the website. You can find it down in the link description, chemcomplete.com. Go over there and pick yourself up a guide if you want to help support the channel and you want to inform yourself. Other than that, remember to subscribe, like if the content helped you, comment, and I'll get back to you. And thank you so much for spending the time to learn with me. I'm out of here until the next one, guys. Take care.